Okay, it's 10:30, so I'm very happy to welcome you to this DIMPACT webinar. So DIMPACT is a project dealing with interaction between breaking waves, energetic waves, and floating offshore wind turbine. And today we'll share some of the results of the project, which is a collaborative project with many partners, as you can see at the bottom. And so I'll start with the agenda. I'll give a short introduction, try to show you a summary of the project, then focus on the main project results with a first talk by Christophe Perra from EDF R&D, who will tell us about the motion and attitude of floating offshore wind turbine in high sea using numerical models. This works actually fed wave tongue experiment and load severity measurements, and this will be presented by Florent Hulin, who is doing his PhD between France Énergie Marine, Ifremer, and ENSTA Bretagne. Then we will have a talk by Paul Renaud from France Énergie Marine, who will deal with the hydrodynamic loads model on floating offshore wind turbine. He will present new slamming loads models, specifically designed for floating offshore wind turbine, and also new approach to assess slamming loads from linear wave properties. And then we'll finish with a talk by Camille Matouk from France Énergie Marine, who will tell us about the implementation of the engineering method from DIMPACT in the open phase tool. So it's quite a well-known problem for bottom fixed offshore wind turbine, and today we will be focusing on the floating offshore wind turbine. So floating offshore wind turbine actually moves in the water, they float, and the surge motion and the tilt of the turbine may affect the slamming loads. And therefore, we actually need to go through fully hydroelastic servo model to understand the slamming scenarios to which floating offshore wind turbine are exposed. I just mentioned the fact that probably the most advanced methods to address this kind of loads on bottom fixed offshore wind turbine were derived in the DERIS project for bottom fixed turbine. So on the right hand side, you have an illustration on breaking wave impact on the offshore wind bottom fixed offshore wind turbine in Denmark. Okay, so I try to give you a bit more of illustration of the problem at hand. So this is a video from the WindFloat Atlantic floating offshore wind turbine from Principal Power. Sorry for the load, for the sound. And you see that illustration of the problem at hand. So breaking waves that is hitting at the foundation of the floating offshore wind turbine. Okay, so it's a very complex simulation. You see that the sea state is very messy. And here, on the right-hand side, you see an illustration of a numerical simulation of a floating offshore wind turbine in high seas. So this kind of simulation are actually very neat. In some ways, they are very complex because they couple the aerodynamic loads, the hydrodynamic loads, the mooring effect, the structural response of the blades of the structure on the floater. So it's a very, very advanced tools. In the meantime, you can see that there are some oversimplifying assumptions, especially for the wave field, which is here a linear wave field on 1D, which is quite far from what you see on the left-hand side, okay? And this is actually one of the main challenges of the project. So the main question is, how can we incorporate slamming loads assessment in floating offshore wind turbine numerical model? So the first question we should ask is first, can we detect breaking waves in these linear sea states? Okay, so I'm introducing some results. I won't give much detail about it, but they will be used all along the other presentations. I think it's important that I give a first insight on this problem. So very quickly, we work on this along the project, and we actually look at what we call the kinematic braking criterion. That is a ratio between U over C, U being the field orbital velocity at the crest, the horizontal field orbital velocity at the crest, and C being the phase speed of the crest. And so what is commonly assumed is that if this criteria reaches the 0.85 value, the wave will inevitably break, following the work from Barthelemy et al. 2018. What we found is by comparing nonlinear wave simulations that are in red here, you have a wave, nearly breaking wave profile, linear equivalent criterion that is U over C equal 0.34, meaning that theoretically we are able to detect breaking wave within this very simple linear system. The next question that is very fundamental for this project is, can we assess the breaking severity from the linear wave properties? Meaning, can we assess the magnitude of the load that would be induced by breaking wave just knowing the properties of these linear waves? So for this, we use a parameter called the gamma parameter derived by Derecki et al. 2018 that was shown to relate to the breaking wave dissipation and therefore to the breaking wave severity. And we did the same kind of work as one done for with the top illustration here. So we compared the gamma value we obtained for the nonlinear waves, so let's say the real one, and for the linear one. And we obtained a very good correlation, meaning that we have a model to go from linear waves to nonlinear wave for the severity. And just to give you a bit more of illustration regarding this, so low gamma value means filling breaker, high gamma value means plunging breaker here. Of course, these one are much more dangerous for structure at sea. Okay, so and these results are being written in papers in preparation that hopefully will be released soon by Florian Hulin and also Marc Prévosto and colleagues of the project. Okay, so very quickly, we achieved different other scientific breakthroughs through the project. A new wave loads model for the hydrodynamic loads, loads that account for the moving and tilted motion of the floating offshore wind turbine. We obtained also a new vibration correction method for hydrodynamic loads, and also other achievements in terms of scientific results. And also, it's important to note that this method to account for wave load on moving tilted cylinder will be referred to in the 2024 update of the DNV RPC 205 recommended practice, which is a nice transfer to the industry of the project results. So using this, all these scientific results, we built a full method to assess design wave loads using global FOWT models. So what we did is using this relation between linear and nonlinear world, using also wave tank experiment results connecting the gamma parameter to the wave loads measured on the cylinder. We came up with a total force model that gives us for any sea state, just knowing simple parameter of the sea state, typically significant wave height and peak period, we are able to define the load potential of the sea state. So then we can apply this load model to the site of interest, to the climatology of the site of interest, to obtain this kind of distributions, from which we can derive the 50-year return value of the slamming load or the wave load potential of on the site, which enables us to derive the design sea states candidate that should be played within the FOWT model. Then, knowing properties from the linear waves that is propagating within this model, and knowing the attitude of the cylinder of the floating offshore wind turbine, we were able to derive a new load model that is implemented in this type of FOWT coupled models that give us a design load. So that's the main achievement of the project here, to be able to derive a full methodology that is, we believe, quite consistent. And so we'll go through some of the scientific results that enables us to achieve this full methodology. Okay, just I'm a bit late here already, but a few words about the applicability of the results. So it should work on any floating substructure made of vertical cylinders. but also any bottom fixed structure made of vertical cylinders, so any bottom fixed wind turbine. Site condition, we do not have any limitation in terms of water depth from a theoretical point of view. Any wave condition should work. Of course, it is designed for slamming loads and breaking waves. And variable bathymetry might be a problem that we need to explore with these linear approaches. Okay, so here just an overview of the publication that explain the results that we are developing the project.